This is section 2.2, part B, polynomial functions. Your I can statements for this function: I can graph polynomial functions, and I can model real-world data with polynomial functions. The multiplicity of a polynomial function tells us how many times a specific x value is a zero of the function. So if we take a look at the example, remember to determine the zeros, you're going to set each part equal to 0. So if I set x cubed equal to 0, x will just equal 0. But there are actually 3 x's there. So 0 will occur 3 times. So it has a multiplicity of 3. X minus 4 will set it equal to 0. So x is equal to 4. But that quantity is actually squared. So that's happening 2 times. So that will have a multiplicity of 2. And x plus 1 you would set equal to 0. So x is equal to negative 1. And that just has a multiplicity of 1. So if we take a look at this function, we're going to apply the leading term test to determine what the n behaviors are going to do. We're going to determine the zeros, and we're going to state the multiplicity if any of them repeat. We're going to find a few additional points, and then we're going to go ahead and graph it. So to determine your leading term, you can basically just see how many x's you are going to have, and then see what exponent is going to be in front of it when it's written in this form. So these x's, I have 2 of them here. So I have 2 x's from here. If I multiply it by this one, we're gaining another x, so now we're up to x to the 3rd. And then when we multiply it by the x out front, that gets us 1 more. So we know that's going to be x to the 4th. If we see what the value in front of that would be, I have a 1 here. 1 times 2 is 2, and 2 times 1 is still 2. So our leading term is going to be 2x to the 4th for this function. You can actually multiply all of this out and see what the entire function would look like, but we only need the leading term. So if our leading term is 2x to the 4th, we know our n value is 4, which is even. We know that our leading coefficient is 2, which is positive. So we do know that both ends of our function will be going up because it's even, they go the same direction. Since it's a positive leading coefficient, we know that they will be going up. Now we need to determine the zeros and the multiplicity of the zeros. So we have x is equal to 0. We have 2x plus 3 is equal to 0. And we have x minus 1 is equal to 0. On the first one, x is just equal to 0, so you can go ahead and graph that point. On the next one, to get the x by itself, we're going to subtract that 3. Then we're going to divide both sides by 2, so we get x is equal to negative 3 over 2. So we know it's going to cross the x-axis at negative 1.5. And if we get the last one by itself, to move the 1, we're going to add it to both sides. So we get x is equal to 1. But if you notice, this quantity is squared, so this one will have a multiplicity of 2. When you go to graph that, you do only graph that once, but it does have that multiplicity of 2. Let's go ahead and change the scale a little bit so we make each one of these worth a half going across. So if we regraph this, I have a point here, I have a point here, and I have a point here. It does say to find a few additional points. So we can make a table that has data points that are to the left of these values and in between to these values. So if we graph at negative 2, that's at 18. That's not going to fit on our graph. Let's just go ahead and make this 1, 2, 3, 4. If we graph at negative 1, that is at negative 4. If we graph at 0.5, We are at 0.5. So this is positive. We do know that it's going to be going up here, and we know it's going to be going up here because the two ends go up. We're going to hit the points between, and our graph should look like this. So the average personal savings as a percent of disposable income in the United States is given in the table below. So that's the percent they put into savings. In 1970, they put 9.4%. In 2005, there was actually a negative 0.4. So people were taking money out of their savings to use as their spending money instead of putting money in. So the first thing we want you to do is to create a scatter plot of this data to determine the type of polynomial function that can be used to represent the data. To simplify our list, instead of putting in the years of 1970 and 1980, let's call 1970 our year 0. 1980 would then be 10 years from that. 1990 is 20 years, so on and so forth. And so we get up to 2005, which is 35 years later. So in your list 1, you'll put in the 0, 10, 20, 25. In your list 2, you'll put in the percent of savings. Remember to put in values into your list. You're going to hit the Stat button. Then you're going to select Edit. And then you'll put the values into list 1 and the values into list 2. Once you have your two lists into your calculator, you need to make sure your stat plot is turned on. So you're going to hit second, y equals. You're going to select the first plot, make sure it's turned on, make sure it's on scatter plot, make sure your x list is L1 and your y list is L2. Once this is done, you can hit zoom and select zoom stat, which is number 9. So it's going to change your window to fit your statistics. And the graph of this roughly looks like this. So we need to determine what shape this looks like. If you notice, it is going this type of direction. So this is an even function because the ends are going the same direction. So let's go ahead and call this a quadratic. So to write an equation for a quadratic, you're going to hit catalog. So you're going to hit second, 0. This is a quadratic regression. So we're going to go down to our Q's, and we're going to select quad reg. So QUADREG. We're going to put in list 1. So if you hit second stat, that's going to select your list. You select list 1, comma, your list 2, comma, and then your y1. So you would hit vars, yvars, select function, and select your y1. And then if you hit enter, it will give you a quadratic regression. It's going to be in the form of y is equal to ax squared plus bx plus c. And it's going to tell you the values of your a, b, and c so that you can plug them in. So our a value is negative 0.0086. So we can say our b value is 0.0333. And our c value is 9.744. Now this should make sense because our leading coefficient over there is a negative value, and this is squared. So we know that it is pointing down because it's negative, which our graph is pointing down. So on part B, it says write a polynomial function. We've just done that. On C, we're going to use the model to estimate the percent of savings in 1993. So 1993, if we take a look at our numbers, 1993 is 23 years after 1970. So we would plug in 23 into our X value. Now that did put all of that information into your Y equals for you. So you can still hit your vars, Y vars, select your Y equals, put in your number value of X is equal to 23 and hit enter on your calculator, and it will give you that percent for you. So that is going to give us a percent in 1993 of 5.94% of their money is going into savings. On part D, we need to use the model to determine the approximate year in which the percent of savings reaches 6.5. To do this, you can go back to your Y equals, and in your Y2, you can just graph a constant line of 6.5. That's going to tell you a Y value of 6.5%. If you graph that on the same graph as your stat plot and your quadratic regression, where those two values cross is where you will find your year. So if you trace until you get to where those two lines cross, and those two lines cross at about X value of 21. So if they cross at 21, 1970 plus 21 years is going to give us 1991. So in 1991, they will reach a savings of about 6.5%.